P2PKH transactions. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics, with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into one of Bitcoin's most fundamental transaction types, pay-to-public key hash, or P2PKH. This transaction type has been the backbone of Bitcoin since its inception and remains the most commonly used format for sending and receiving Bitcoin. Understanding P2PKH is absolutely essential for anyone wanting to grasp how Bitcoin transactions work at a technical level. P2PKH transactions represent approximately 70% of all Bitcoin transactions historically, making them the de facto standard for peer-to-peer value transfer. The beauty of P2PKH lies in its elegant simplicity, combined with robust security through cryptographic hashing. Rather than sending coins directly to a public key, P2PKH adds an extra layer of protection by hashing the public key. This provides several advantages, including reduced transaction size and enhanced security against certain types of attacks. In this comprehensive presentation, we will explore every aspect of P2PKH transactions. We will cover the fundamental concepts of addresses and keys, the detailed structure of transaction inputs and outputs, and the step-by-step process of creating, signing, and verifying these transactions. We will use detailed mermaid diagrams to visualize the data flow at each stage, ensuring you understand not just what happens, but also why it happens and how all the pieces fit together. What is P2PKH? Pay-to-public key hash, abbreviated as P2PKH, is a Bitcoin transaction script pattern that allows you to send Bitcoin to a recipient's hashed public key rather than directly to their public key. This might sound like a subtle distinction, but it has profound implications for both security and efficiency. The fundamental concept behind P2PKH is layered cryptographic protection. When you want to receive Bitcoin, you don't expose your actual public key in the blockchain until you spend those coins. Instead, what gets recorded in the blockchain is a cryptographic hash of your public key, combined with some additional data to form what we call a Bitcoin address. This hash is created using two sequential hash functions. First SHA-256, then RIPEMD-160. Resulting in a 160-bit hash value that we call the public key hash, or pub key hash. The P2PKH transaction structure consists of two main components: the ScriptPubKey in the transaction output, which defines the spending conditions, and the ScriptSig in the transaction input, which provides the proof that those conditions have been met. The ScriptPubKey essentially says whoever can provide a public key that hashes to this specific value, and can provide a valid signature from the corresponding private key, can spend these coins. This creates a challenge-response mechanism that is both elegant and secure. One of the key advantages of using a hash instead of the raw public key is quantum resistance, at least partially. While a quantum computer could theoretically derive a private key from a public key using Shor's algorithm, it cannot reverse a cryptographic hash function. As long as your public key remains hidden behind its hash, your coins have an additional layer of protection against future quantum attacks. Of course, once you spend coins and reveal your public key in the ScriptSig, that particular output loses this protection. This is why Bitcoin best practices recommend never reusing addresses. P2PKH address structure. Bitcoin addresses are not just random strings of characters. They have a very specific structure that serves multiple purposes, including error detection, version identification, and human readability. Let's break down exactly how a P2PKH address is constructed from a public key, step by step. The journey from public key to Bitcoin address involves several cryptographic operations. Starting with your ECDSA public key, which is a point on the SEC P256K1 elliptic curve represented as a 65-byte uncompressed value or a 33-byte compressed value. We first apply SHA-256 hashing. The SHA-256 algorithm produces a 256-bit hash output. We then take this SHA-256 hash and apply RIPEMD160, which reduces the hash to 160 bits or 20 bytes. This two-step hashing process is called hash 160 in Bitcoin terminology. To this 20-byte hash, we prepend a version byte. For mainnet P2PKH addresses, this version byte is 0x00, which will eventually result in addresses starting with the number 1. For testnet P2PKH addresses, the version byte is 0x6f, resulting in addresses starting with M or N. This version byte allows Bitcoin software to immediately identify what type of address it is dealing with and which network it belongs to. Next comes the checksum, which is crucial for error detection. We take the version byte, plus the public key hash, and apply SHA-256 twice, a process which is called double SHA-256. From this resulting 32-byte hash, we take only the first 4 bytes. These 4 bytes serve as a checksum that will help detect typos or transmission errors when someone enters or copies the address. If even a single character in the address is wrong, the checksum validation will fail, preventing users from accidentally sending Bitcoin to an incorrect address. Finally, we concatenate the version byte, the 20-byte public key hash, and the 4-byte checksum, giving us 25 bytes total. This byte string is then encoded using base 58 check encoding, a custom encoding scheme designed by Satoshi Nakamoto that uses 58 alphanumeric characters, specifically excluding characters that look similar to each other such as 0 and O, or I and L. The result is the familiar Bitcoin address format, like beginning with 1A, ending with NA, which is Satoshi's own address from the Genesis block. This entire process ensures that Bitcoin addresses are both secure and user-friendly. P2PKH transaction structure. A Bitcoin transaction is fundamentally a data structure that transfers value from transaction inputs to transaction outputs. In P2PKH transactions, this structure follows a specific format that includes version numbers, input and output arrays, witness data in the case of SegWit, and a locktime field. Understanding this structure is essential for anyone working with Bitcoin at a technical level. Every transaction begins with a 4-byte version number, currently set to either 1 or 2 for most transactions. Version 2 became standard with BIP68, which enabled relative lock times. The version number allows for future protocol upgrades and tells nodes how to interpret the transaction data. Following the version is the input count, a variable length integer that specifies how many inputs this transaction is consuming. Each input in a P2PKH transaction contains several critical fields. The previous transaction hash, or TXID, is a 32-byte hash that identifies which earlier transaction created the output being spent. The output index, or VOUT, is a 4-byte integer specifying which specific output from that previous transaction we are spending, since transactions can have multiple outputs. The ScriptSig field contains the unlocking script that proves ownership, which for P2PKH includes a signature and the public key. Finally, the sequence number is a 4-byte field originally intended for transaction replacement but now used primarily for relative locktime functionality. After all inputs are specified, the transaction includes an output count, followed by the actual outputs. Each output has 2 main components: an 8-byte value field specifying the amount of Satoshis being sent, and a script public key that defines the conditions that must be met to spend this output in a future transaction. For P2PKH outputs, this script contains the hashed public key of the recipient and the instructions for how to unlock these funds. The transaction concludes with a 4-byte locktime field, which can specify either a block height or a Unix timestamp before which the transaction cannot be included in a block. A lock time of 0 means the transaction can be included immediately. This entire structure must be serialized in a specific byte order, hashed, and signed to create a valid Bitcoin transaction that nodes will accept and miners will include in blocks. ScriptPubKey Deep Dive. The ScriptPubKey, also called the locking script, is the heart of Bitcoin's programmable money concept. It defines the conditions that must be satisfied to spend an output, creating a cryptographic puzzle that only the intended recipient can solve. For P2PKH transactions, this script follows a standard template that has proven both secure and efficient over Bitcoin's history. A P2PKH ScriptPubKey consists of exactly 5 opcodes and data elements, totaling 25 bytes. Let's examine each component. The script begins with op-dup, which duplicates the top item on the stack. Following this is op#160, an opcode that performs #160 operation, which, as we discussed earlier, means SHA-256 followed by RIPEMD-160 on the top stack item. Next, a data push of 20 bytes provides the actual public key hash of the recipient. This is the critical piece of information that identifies who can spend these coins. After the public key hash comes OP=verify, a combined operation that checks if the 2 top stack items are equal, and if so, removes them from the stack and continues execution. If they are not equal, the script fails immediately and the transaction is invalid. Finally, the script ends with OP_check_sig, which verifies that a valid signature has been provided for the public key and the transaction data. The complete P2PKH ScriptPubKey, in hexadecimal, looks like this, beginning with 76 ending with 14, followed by the 20-byte public key hash, and then followed by beginning with 88 ending with a C. Let's break down these hexadecimal values. 76 is op-dup. A9 is op#160. 14 indicates a data push of 20 bytes, which is then followed by the actual 20 bytes of the public key hash. 88 is op=verify, and AC is op_check_sig. This standardized format allows Bitcoin software to quickly identify P2PKH outputs and process them efficiently. What makes this script particularly clever is its use of cryptographic operations to verify ownership without revealing the actual private key. The recipient must provide both their public key and a signature, but the public key is not known to the network until they spend the output. This delayed revelation provides an extra security layer, particularly important given potential future advances in cryptanalysis or quantum computing. ScriptSig Deep Dive. The ScriptSig, or unlocking script, is provided by the spender to satisfy the conditions set by the ScriptPubKey. In P2PKH transactions, the ScriptSig is relatively straightforward but contains critical cryptographic proof of ownership. Understanding how this script is constructed and validated is essential to understanding Bitcoin security. A P2PKH ScriptSig contains exactly 2 elements, a signature and a public key, in that order. The signature is an ECDSA digital signature created by signing the transaction hash with the private key corresponding to the public key hash in the ScriptPubKey. This signature is typically 71 to 73 bytes long, though the exact length can vary slightly. The signature includes a signature hash type byte at the end. This is usually SI#all, which is 0x01. Indicating that the signature covers all inputs and outputs of the transaction. The signature generation process is mathematically complex but conceptually straightforward. The transaction data is serialized in a specific format, excluding the script SIGs from all inputs. This serialized data is then double-hashed with SHA-256, producing a 32-byte message hash. The private key is then used with the ECDSA signing algorithm to produce a signature for this hash. The signature consists of 2 numbers, R and S, which are encoded using DER format, a standard for encoding cryptographic signatures. Following the signature in the ScriptSig is the full public key, which is either 65 bytes for an uncompressed key or 33 bytes for a compressed key. Compressed keys have become the standard because they save space on the blockchain while providing the same security. The public key is prefixed with either 0x04 for uncompressed keys, or 0x02 or 0x03 for compressed keys. This prefix indicates the format and, for compressed keys, the parity of the y coordinate. The complete ScriptSig is serialized by first pushing the signature length, then the signature bytes, then pushing the public key length, then the public key bytes. When this ScriptSig is combined with the ScriptPubKey during validation, Bitcoin's scripting engine executes them together on a stack-based virtual machine. The ScriptSig is executed first, placing the signature and public key on the stack. Then the ScriptPubKey executes, using these values to verify that the spender truly controls the private key associated with the hashed public key. If all operations succeed and the stack ends with a true value, the input is considered valid. Complete script execution flow. Understanding how Bitcoin validates a P2PKH transaction requires following the step-by-step execution of the combined ScriptSig and ScriptPubKey on Bitcoin's stack-based scripting engine. This process is deterministic, meaning it will always produce the same result for the same inputs, which is crucial for network consensus. The script execution begins with an empty stack. The ScriptSig executes first, pushing the signature and then the public key onto the stack. At this point, the stack contains two elements: the signature at the bottom and the public key on top. This is the initial state before the ScriptPubKey begins execution. Now the ScriptPubKey key takes over. The first opcode is OP_dup, which duplicates the top stack item. Since the public key is already on top, we now have two copies of the public key on the stack, with the signature still at the bottom. Next comes OP#160, which pops the top item from the stack, performs SHA-256, followed by RIPEMD-160 on it, and then pushes the result back. At this point, the stack contains the signature, the public key, and the hash of the public key. The ScriptPubKey then pushes the expected public key hash onto the stack, the one that was included in the locking script when this output was created. Now we have four items on the stack: signature, public key, computed hash, and expected hash. The OP=verify opcode pops the top two items, the computed hash and expected hash, and compares them. If they are not equal, the script fails immediately and the transaction is rejected. If they are equal, execution continues, and now only the signature and public key remain on the stack. Finally, OP_check_sig executes. This is the most computationally intensive operation in the script. It pops both the public key and the signature from the stack. It then reconstructs the transaction hash that should have been signed, and uses the ECDSA verification algorithm to check if the signature is valid for that hash and that public key. If the signature is valid, OP_check_sig pushes true onto the stack. If invalid, it pushes false. For the transaction to be valid, the stack must end with a true value after all operations complete. This entire process ensures that only someone with the correct private key could have created the signature, proving ownership of the funds. Creating a P2PKH transaction. Creating a P2PKH transaction involves several detailed steps, from selecting which outputs to spend, through constructing the transaction structure, to signing the inputs and broadcasting to the network. Each step requires precision and understanding of Bitcoin's consensus rules. The process begins with UTXO selection. UTXO stands for unspent transaction output, and these are the coins in your wallet that you can spend. Your wallet software needs to select which UTXOs to use as inputs for your transaction. This selection process can use various algorithms such as first in first out, largest first to minimize fees, or coin selection algorithms that optimize for privacy. The total value of selected UTXOs must be greater than or equal to the amount you want to send plus the transaction fee. Next, you construct the transaction structure. This means specifying the version number, typically 2 for modern transactions, creating the input array with references to the UTXOs being spent, and creating the output array with the recipient's address and amount. If the total input value exceeds the output value plus fee, you must create a change output that sends the excess back to one of your own addresses. The difference between total inputs and total outputs is the transaction fee that goes to the miner. Before signing, you need to prepare the transaction for signature generation. For each input, you create a version of the transaction where that input ScriptSig is temporarily replaced with the ScriptPubKey of the output being spent. All other ScriptSigs are set to empty. You then append the SCI hash type, typically SCI hash_all, which is 0x01 as a 4-byte little Indian integer. This entire structure is then double hashed with SHA-256 to produce the message hash that will be signed. The signing process uses your private key and the ECDSA algorithm to create a signature for each input. The signature is then DER encoded and the SCI hash type byte is appended. This signature, along with your public key, forms the ScriptSig for that input. This process is repeated for each input in the transaction. Once all inputs are signed, the transaction is complete and ready to be serialized into its final byte format. The final step is broadcasting the transaction to the Bitcoin network. Your wallet software connects to one or more Bitcoin nodes and sends the serialized transaction using the Bitcoin peer-to-peer protocol. These nodes validate the transaction, checking signatures, ensuring inputs haven't been spent before, verifying sufficient fees, and checking all consensus rules. If valid, they add it to their mempool and relay it to other nodes. Eventually, a miner will include your transaction in a block, and after that block is mined and confirmed, your transaction is permanently recorded in the blockchain. Transaction data flow. Understanding the complete data flow in a P2PKH transaction, from the moment coins are received to when they are spent, provides crucial insight into Bitcoin's architecture. This flow demonstrates how Bitcoin achieves both security and decentralization through its carefully designed protocol. The journey begins when someone sends you Bitcoin. They create a transaction output with a ScriptPubKey containing your public key hash. This transaction is broadcast to the network, validated by nodes, included in a block by a miner, and confirmed as the block is added to the blockchain. At this point, you have a UTXO, an unspent transaction output, that you can spend in a future transaction. Your wallet detects this UTXO by monitoring the blockchain for outputs containing your public key hashes. When you decide to spend these coins, your wallet constructs a new transaction that references this UTXO as an input. The reference consists of the transaction ID of the transaction that created the UTXO, and the output index within that transaction. Your wallet then creates the ScriptSig, which involves generating a signature using your private key. This signature is created by signing a hash of the transaction data, ensuring that the signature is specific to this exact transaction and cannot be reused for a different transaction. The transaction data flows through several transformations during creation. First, the raw transaction structure is created with all the inputs and outputs. Then, for each input, a modified version of the transaction is created for signing purposes. This modified version is hashed to create the message digest that gets signed. The resulting signature and public key are inserted into the ScriptSig field of that input. This process repeats for each input, potentially with different private keys if the inputs came from different addresses. Once fully constructed and signed, the transaction is serialized into a byte stream following Bitcoin's exact serialization format. This includes specific byte orderings, variable length integers for counts, and the precise structure of each field. The serialized transaction is then hashed with double SHA-256 to create the transaction ID, which is a unique identifier for this transaction. This transaction ID is what will be used in future transactions that spend outputs from this transaction. The transaction then enters the peer-to-peer network layer, where it is broadcast from node to node. Each node that receives it performs full validation. This includes executing all scripts, checking all signatures, verifying that inputs exist and have not been spent, and ensuring that all consensus rules are followed. Valid transactions then enter the mempool, which is a waiting area for unconfirmed transactions. Miners select transactions from the mempool, typically prioritizing those with higher fees, and include them in candidate blocks. When a miner successfully mines a block containing your transaction, the data flow completes, and your transaction becomes part of Bitcoin's permanent ledger, the blockchain. Input construction details. The construction of transaction inputs in P2PKH transactions requires careful attention to detail, as each field must be formatted precisely according to Bitcoin's consensus rules. Any deviation will result in the transaction being rejected by the network. Let's examine each field that comprises a transaction input. The previous transaction hash field, also called the outpoint TXID, is a 32-byte hash that identifies the transaction containing the output being spent. This hash is stored in Little Endian byte order, which means the bytes are reversed from how they typically appear in block explorers and Bitcoin software. For example, if a transaction ID appears as beginning with a B ending with 34 in a block explorer, it will be stored as beginning with 34 ending with a B in the actual transaction data. This byte order reversal is a quirk of Bitcoin's implementation that developers must account for. Following the transaction hash is the output index, a 4-byte unsigned integer in Little Endian format. This index specifies which output from the previous transaction is being spent, starting from 0. If the previous transaction had 3 outputs and you are spending the second one, this field would contain the value 1. This combination of transaction hash and output index uniquely identifies a specific UTXO on the blockchain. The ScriptSig length is encoded as a variable length integer or variant. This is an efficient way to encode integers that might be small or large. For values less than 253, it is a single byte. For values from 253 to 65,535, it is 0xFD followed by 2 bytes. For larger values, the prefixes 0xFE and 0xFF are used for 4-byte and 8-byte integers, respectively. For typical P2PKH inputs, the ScriptSig is around 107 bytes for compressed public keys, or 139 bytes for uncompressed. So, a single byte variant suffices. The ScriptSig itself, as we discussed earlier, contains the signature and public key. The signature includes a DER-encoded ECDSA signature followed by a SIG hash-type byte. The public key is either the 33-byte compressed format or 65-byte uncompressed format. Both the signature and public key are prefixed with their lengths as single-byte push operations, which are opcodes in the Bitcoin script that tell the interpreter how many bytes to read for each element. Finally, each input concludes with a sequence number, a 4-byte unsigned integer. Originally, this was intended to allow transaction replacement before confirmation, but this functionality was disabled early in Bitcoin's history due to potential security issues. The sequence number was repurposed with BIP68 to enable relative lock time functionality. A sequence number of beginning with 0x, ending with FF signals that the input is finalized and cannot be replaced. Lower values can indicate relative lock times when combined with BIP68 and BIP112. For standard transactions without time lock requirements, the sequence is typically set to beginning with 0x, ending with FF. Output construction details. Transaction outputs in P2PKH transactions are conceptually simpler than inputs, but their precise construction is equally critical for creating valid transactions. Each output consists of 2 main components: a value field specifying the amount of Bitcoin being sent, and a ScriptPubKey defining who can spend it. The value field is an 8-byte signed integer in Little Endian format, specifying the amount in Satoshis. A Satoshi is the smallest unit of Bitcoin, equal to 0.00000001 BTC, since 8 bytes can represent numbers up to 2 to the power of 63-1 when using signed integers. This allows for a maximum value of approximately 9.2 quintillion Satoshis, which far exceeds Bitcoin's total supply limit of 21 million coins. In practice, Bitcoin's consensus rules enforce a maximum output value of about 21 million BTC, or 2.1 quadrillion satoshis. The value must be a positive integer. Negative or zero values are invalid for standard outputs. However, there is an exception for OP return outputs, which are used for data storage and can have zero value. For P2PKH outputs, the value must be at least 546 satoshis for the output to be considered non-dust by most node policies. Although this is not a consensus rule, it is a relay policy to prevent blockchain bloat with economically insignificant outputs. Following the value is the ScriptPubKey length, again encoded as a variable length integer. For P2PKH outputs, this is always 25 bytes, so the variant is simply the single byte beginning with 0x ending with 19 in hexadecimal. This length includes all the opcodes and data in the ScriptPubKey. The ScriptPubKey for P2PKH, as we have discussed, is the 25-byte script that contains the spending conditions. This begins with OP_DUP followed by OP#160, then a 20-byte data push of the recipient's public key hash, then OP=verify, and finally OP_check_sig. This exact sequence must be followed for the output to be recognized as a standard P2PKH output by Bitcoin software. When creating multiple outputs in a single transaction, such as sending Bitcoin to a recipient while also creating a change output back to yourself, each output is completely independent. The order of outputs in the transaction is arbitrary and doesn't affect validity, though some wallets order them in specific ways for privacy reasons. For example, some wallets randomize output order to make it harder for blockchain analysis to determine which output is the change and which is the payment. Signature generation process. The signature generation process for P2PKH transactions is one of the most critical and complex aspects of creating valid Bitcoin transactions. This process ensures that only the holder of the private key can authorize spending of the associated outputs, providing the fundamental security guarantee of Bitcoin. Signature generation begins with transaction serialization for the signing process. This is a modified version of the transaction. Here, the ScriptSig of the input being signed is replaced with the ScriptPubKey of the output being spent. All other inputs have their ScriptSigs set to empty. This modification is crucial because we are signing a version of the transaction that includes the spending conditions we are trying to satisfy. This process prevents certain types of signature malleability attacks. The SIGHASH type is then appended to this serialized transaction as a 4-byte little endian integer. The most common SIGHASH type is SIGHASH-ALT, which has the value 0x01. This indicates that the signature covers all inputs and all outputs, meaning the signature becomes invalid if any part of the transaction is modified. Other SIGHASH types include SIGHASH-none, which does not sign any outputs, and SIGHASH-single, which signs only the output with the same index as the input. There is also SIGHASHANYONECANPAY, which can be combined with the others and indicates that the signature only covers one input. This modified transaction is then hashed using double SHA-256, meaning SHA-256 is applied 2 times in a row. This results in a 32-byte hash value that serves as the message being signed. This hash is deterministic, meaning that the same transaction data will always produce the same hash, a key factor for verification. The actual signing uses the elliptic curve digital signature algorithm, specifically the SEC P256K1 curve that Bitcoin uses. The private key, which is a 256-bit number, is used with the message hash to generate a signature consisting of 2 values, R and S. The R value comes from a random K value chosen during signing and represents the X coordinate of a point on the elliptic curve. The S value is calculated using the private key, the message hash, and K. The specific formulas are R equals the X coordinate of K times the generator point G, and S equals K inverse times the quantity message hash plus R times the private key, all modulo the curve order. The K value must be truly random and must never be reused across different signatures. If K is ever reused or predictable, an attacker can extract the private key from two signatures. This is what happened in the famous PlayStation 3 hack where Sony reused K values, allowing hackers to recover Sony's signing key. For this reason, modern Bitcoin implementations use deterministic K generation according to RFC 6979, which derives K from the private key and message in a deterministic but unpredictable way. The resulting R and S values are then encoded using distinguished encoding rules, or DER, which is a standard way to encode signatures. The DER format includes type tags, length fields, and padding to ensure the values are encoded unambiguously. The SIASH type byte is appended to the end of this DER encoded signature, creating the final signature that goes into the ScriptSig. This entire process must be repeated for each input in the transaction, though each can potentially use a different private key if the inputs come from different addresses. Signature verification process. When a Bitcoin node receives a transaction, it must verify all signatures to ensure the transaction is valid and that the spender actually controls the private keys for the inputs being spent. This verification process is performed independently by every full node in the network, ensuring decentralized consensus without trust. Verification begins by extracting the signature and public key from the ScriptSig. The signature is DER decoded to extract the R and S values, and the SIASH type byte is noted. The node then reconstructs the same modified transaction that was signed, following the exact same serialization process used during signing. This includes replacing the current input ScriptSig with the ScriptPubKey from the output being spent, setting other ScriptSigs to empty, and appending the SIASH type. This reconstructed transaction is then double-hashed with SHA-256 to produce the message hash, exactly as was done during signing. At this point, the node has three pieces of information: the message hash, the signature consisting of R and S values, and the public key. These are all that's needed for ECDSA verification. The ECDSA verification algorithm checks whether the signature is valid for the given message hash and public key. Mathematically, it calculates several values. First, it computes W equals the modular inverse of S. Then it calculates U1 equals the message hash times W, and U2 equals R times W. It then computes the point P equals U1 times G plus U2 times the public key, where G is the generator point on the SEC P2PKH curve. If P's x-coordinate modulo the curve order equals R, the signature is valid. If not, it is invalid. This process works because the mathematics of elliptic curve cryptography ensures that only someone with knowledge of the private key could have produced values for R and S that satisfy this equation. An attacker attempting to forge a signature would need to solve the discrete logarithm problem on the elliptic curve. This is computationally infeasible with current technology. After verifying the signature cryptographically, the node also executes the full script to ensure all conditions are met. For P2PKH, this means verifying that the provided public key's hash matches the expected public key hash within the ScriptPubKey. The node also checks various other transaction validity rules, ensuring inputs reference existing unspent outputs, verifying that output amounts do not exceed input amounts, checking that the transaction size is within limits, and confirming that all consensus rules are satisfied. Only after all these checks pass is the transaction considered valid and allowed into the node's mempool or accepted in a block. Transaction fees and change. Understanding transaction fees and change outputs is essential for creating P2PKH transactions that will be confirmed in a reasonable time and don't waste your Bitcoin. The fee mechanism is how Bitcoin incentivizes miners to include transactions in blocks, and proper change handling is crucial for maintaining control of your funds. Transaction fees in Bitcoin are implicit rather than explicit. There is no fee field in the transaction structure. Instead, The fee is calculated as the difference between the sum of all input values and the sum of all output values. If your inputs total 0.5 BTC and your outputs total 0.499 BTC, the fee is 0.001 BTC or Satoshis. This fee goes to the miner who includes your transaction in a block as part of the Coinbase transaction. Fee rates are typically expressed in Satoshis per virtual byte, or SAT per VB. A virtual byte is a weight unit used since the SegWit upgrade, where witness data is discounted. For legacy P2PKH transactions, bytes and virtual bytes are equivalent. The total fee is the transaction size in bytes multiplied by the fee rate. A typical P2PKH transaction with one input and two outputs is about 225 bytes, so at a fee rate of 50 SAT per VB, the fee would be 11,250 Satoshis. Fee rates vary significantly based on network congestion. During periods of high demand, users compete for limited block space by offering higher fees. Miners typically prioritize transactions with higher fee rates, as they aim to maximize their income. During quiet periods, fee rates can drop to just 1 SAT per VB. Your wallet software usually estimates an appropriate fee rate based on recent blocks and current mempool conditions. However, you can typically override this with a custom fee. Change outputs are necessary when your input values exceed what you want to send plus fees. For example, if you have a UTXO worth 1 BTC and want to send 0.3 BTC with a 0.0001 BTC fee, you need to create a change output of 0.6999 BTC that sends the excess back to your own wallet. This change output is a regular P2PKH output to an address you control, typically a new address generated by your wallet for privacy reasons. The change address should ideally be a fresh address that hasn't been used before. This improves privacy by making it harder for observers to determine which output is the payment and which is change. Some wallets implement sophisticated change handling strategies, such as creating multiple change outputs or choosing change addresses that don't obviously link back to the original sender. One important consideration is dust outputs. Bitcoin's relay policies typically reject outputs smaller than 546 Satoshis as dust because they cost more in fees to spend than they are worth. If your change would be dust, it is better to add it to the fee rather than creating an unspendable output. Well-designed wallet software automatically handles this, either by increasing the fee to consume the dust or by selecting different inputs to avoid the situation entirely. Transaction validation flow. When a Bitcoin node receives a transaction, it performs an extensive series of validation checks before accepting it into its mempool or confirming it in a block. Understanding this validation flow is crucial for debugging transaction issues and understanding Bitcoin's security model. Validation begins at the syntactic level. The node first checks that the transaction is well-formed. This means ensuring the version number is valid, the input and output counts match the actual number of inputs and outputs, all variable length integers are properly formatted, and the total serialized size does not exceed the maximum transaction size of 100,000 bytes for standard transactions. Any malformation at this level causes immediate rejection without further processing. Next comes contextual validation of the inputs. For each input, the node looks up the previous transaction output being spent in its UTXO set. This is a database maintained by full nodes that tracks all unspent transaction outputs. If the referenced output does not exist or has already been spent, the transaction is invalid. This is how Bitcoin prevents double spending. Once an output is spent, it is removed from the UTXO set and can never be spent again. The node then verifies that the sum of input values is greater than or equal to the sum of output values. The difference is the transaction fee, which must be non-negative. If outputs exceed inputs, the transaction is creating money out of thin air, which is obviously invalid except in the special case of Coinbase transactions that miners create. Script execution comes next. For each input, The node executes both the ScriptSig and ScriptPubKey together on Bitcoin's stack-based virtual machine. For P2PKH inputs, this means pushing the signature and public key onto the stack, then executing the OP-DUP, OP-160, hash comparison, and OP-check-SIG sequence. The OP-check-SIG operation is particularly intensive as it requires ECDSA signature verification, which involves elliptic curve point multiplication. If any script fails or leaves anything other than true on the stack, the entire transaction is invalid. Additional consensus rules are checked. For example, lock time validation if the transaction has a non-zero lock time, and sequence number checks for relative lock time functionality. The node also applies local policy rules, for example, minimum fee rates, maximum script size limits for standard transactions, and dust thresholds. Policy rules can vary between nodes, but consensus rules must be enforced identically by all nodes to maintain network consensus. If the transaction passes all these checks, it is added to the node's mempool and relayed to peers. The transaction remains in the mempool until it is either included in a block or evicted because the mempool fills up with higher fee transactions. Once included in a block that is added to the blockchain and reaches sufficient confirmations, the transaction is considered final, and the outputs become available for spending in future transactions. P2PKH security model. The security of P2PKH transactions relies on multiple layers of cryptographic protection, each serving a specific purpose in the overall security architecture. Understanding these security properties helps you use Bitcoin safely and make informed decisions about key management and address reuse. The foundation of P2PKH security is the elliptic curve discrete logarithm problem. The SECP-256K1 curve used by Bitcoin has the property that, given a point on the curve which represents your public key, it is computationally infeasible to determine what number, your private key, was multiplied by the generator point to produce that public key. Current best algorithms for solving this problem have exponential time complexity, making it impossible with existing or foreseeable classical computers for Bitcoin's 256-bit keys. The use of hash functions adds additional layers of security. Your public key is hashed with SHA-256 and then RIPEMD-160 before being included in your Bitcoin address. This means an attacker doesn't see your public key until you spend an output. SHA-256 is cryptographically secure with no known practical attacks, and the additional RIPEMD-160 hashing provides 160 bits of security. Even if SHA-256 were somehow broken, an attacker would still need to reverse RIPEMD-160, and even if both were broken, they'd still need to solve the discrete logarithm problem to find your private key. This layered approach provides partial quantum resistance. Shor's algorithm, which could theoretically run on a sufficiently large quantum computer, can solve the discrete logarithm problem in polynomial time. However, quantum computers cannot reverse hash functions faster than classical computers using Grover's algorithm, which only provides a quadratic speedup. This means that as long as your public key remains hidden behind its hash, your funds have significantly more protection against future quantum attacks. Once you spend from an address and reveal your public key, this additional protection is lost, which is why best practices recommend never reusing addresses. The signature scheme provides non-repudiation and prevents forgery. ECDSA signatures mathematically prove that someone with knowledge of the private key authorized the transaction. The signature is unique to both the transaction data and the private key, so it cannot be reused for a different transaction. Attempting to modify a signed transaction in any way invalidates the signature, preventing malleability attacks where an attacker might try to change transaction details after it is signed. Bitcoin's script execution environment also contributes to security through its limited, non-Turing complete design. Unlike smart contract platforms with Turing-complete languages, Bitcoin script can't enter infinite loops or have unexpected behavior from complex logic. This simplicity reduces the attack surface and makes it easier to audit and verify that scripts behave as intended. For P2PKH specifically, the standard script template has been battle-tested over Bitcoin's entire history with no known vulnerabilities. However, P2PKH security relies on proper implementation. Private keys must be generated with sufficient entropy from secure random number generators. Signatures must use proper key-value generation to prevent key recovery attacks. Wallet software must correctly implement the signing and verification algorithms. These implementation details highlight why using well-audited, open-source wallet software is crucial for Bitcoin security. Common P2PKH issues and debugging. Even experienced Bitcoin developers encounter issues when creating P2PKH transactions. Understanding common problems and how to debug them can save significant time and prevent loss of funds. Let's explore the most frequent issues and their solutions. Insufficient fees are one of the most common problems. If your transaction fee rate is too low, miners may not prioritize your transaction, leaving it stuck in the mempool for hours or days. The mempool can eventually evict low-fee transactions if it fills up with higher-fee transactions. To avoid this, use a wallet or fee estimation service that monitors current network conditions and recommends appropriate fee rates. If you have already broadcast a transaction with too low a fee, some wallets support replace by fee, or RBF, which allows you to replace the transaction with a higher fee version before it confirms. Signature failures are another common issue, usually caused by incorrect transaction serialization during signing. The serialization format for signing is very specific. The input being signed must have its ScriptSig replaced with the ScriptPubKey of the output being spent. Other inputs must have empty ScriptSigs, and the SIGHASH type must be appended correctly. Any deviation produces a different hash and therefore an invalid signature. When debugging signature issues, carefully compare your serialization with the specification and use test vectors from Bitcoin's test suite. Byte order confusion frequently causes problems for developers. Bitcoin uses little endian byte order for most numeric fields, including transaction hashes, output values, and version numbers. However, transaction IDs are displayed in big endian format in block explorers and wallet interfaces. This means you must reverse the byte order when including a TXID in a transaction input. For example, the TXID beginning with a BCD ending with 34 displayed in an explorer would be beginning with 3412 ending with CDAB in the actual transaction data. Always be aware of which format you are working with. Script errors can be subtle. The most common script issue in P2PKH transactions is providing an incorrect public key that does not hash to the expected public key hash. This causes the OP=verify operation to fail. Another issue is signature malleability, where the signature's S value can be inverted without invalidating it. Bitcoin enforces low S signatures as standard since BIP66, meaning if your S value is greater than half the curve order, you must negate it and adjust the signature accordingly. Input reference errors happen when your transaction refers to outputs that do not exist. This can be because you have the wrong TXID, the wrong output index, or because the output has already been spent. Always verify that the UTXOs you are trying to spend are actually available in the UTXO set before constructing your transaction. Use block explorers or Bitcoin Core's get raw transaction and get TXOut commands to confirm output existence and unspent status. Debugging tools are essential for diagnosing these issues. Bitcoin Core's Bitcoin CLI provides commands like decodraw transaction to examine transaction structure, test mempool except to validate transactions before broadcasting, and sign raw transaction with key for manual transaction signing. The Bitcoin script debugger allows step-by-step script execution to see exactly where and why a script fails. Block explorers can show whether your transaction is in the mempool and what error messages nodes might be reporting. For development, use testnet or regtest networks where mistakes don't cost real money. P2PKH Best Practices. Following best practices when working with P2PKH transactions ensures security, privacy, and efficiency. These practices have evolved over Bitcoin's history based on lessons learned from security incidents, privacy research, and practical experience. Not reusing addresses is perhaps the most important best practice. Once you've spent from an address and revealed your public key, that address has less quantum resistance and is permanently linked in the blockchain to your spending patterns. Generate a new address for every transaction you receive. Modern hierarchical deterministic wallets, specified in BIP32 and BIP44, make this easy by deriving unlimited addresses from a single seed phrase. Use compressed public keys for all new transactions. Uncompressed public keys are 65 bytes while compressed keys are only 33 bytes, saving 32 bytes per input. Over Bitcoin's history, this has saved gigabytes of blockchain space. Compressed keys provide identical security to uncompressed keys because they contain the same information, just in a more efficient encoding. All modern wallets use compressed keys by default. Implement proper fee estimation based on current network conditions. Don't use fixed fee rates or outdated fee recommendations. Query fee estimation APIs or analyze recent blocks to determine appropriate fee rates for your desired confirmation time. During high congestion, you may need to pay significantly more than during quiet periods. Some wallets implement dynamic fee selection where users can choose between fast, medium, or economy confirmation times with corresponding fee rates. For privacy, consider coin control and coin selection strategies. Basic coin control lets you manually choose which UTXOs to spend, preventing your wallet from combining coins from different sources in ways that reveal connections. Advanced strategies include avoiding round numbers that reveal which output is change, using multiple change outputs, and implementing coin selection algorithms that minimize privacy leakage through amount correlation. Validate all inputs thoroughly before signing transactions. Verify that you are spending the correct outputs, sending to the correct addresses, and that the fee is reasonable. A common scam involves malware that replaces recipient addresses in the clipboard. Always visually verify addresses character by character before confirming transactions, especially for large amounts. Some hardware wallets display the full address on their secure screen for verification. Back up your private keys securely, but also back up transaction histories and wallet metadata. A seed phrase backup lets you regenerate your keys, but you may lose transaction labels, contact information, and other metadata. Store backups in multiple secure locations, using encryption for digital backups and considering steel plate backups for seed phrases to survive fire or water damage. Test your backups periodically to ensure they are still accessible and correct. Use appropriate security for different value amounts. For small amounts used in regular transactions, a mobile wallet with standard security might be appropriate. For larger amounts, use hardware wallets that keep private keys isolated from internet-connected devices. For very large amounts, consider multi-signature setups or cold storage in completely offline environments. The security measures should scale with the value at risk. P2PKH versus other transaction types. P2PKH is one of several standard transaction types in Bitcoin. Understanding how it compares to alternatives like P2SH, P2PKH, and P2TR helps you choose the right transaction type for different use cases and understand Bitcoin's evolution. Pay-to-script hash, or P2SH, defined in BIP16, allows spending conditions to be specified as arbitrary scripts rather than just public key hashes. The ScriptPubKey contains a hash of the redeem script rather than a hash of the public key. This enables complex spending conditions like multi-signature wallets, time-locked transactions, and other advanced features. P2SH addresses start with a 3 on mainnet and are 34 characters long. The main advantage over P2PKH is flexibility. The disadvantage is larger transaction sizes when spending, since the full redeem script must be revealed. Pay-to-witness public key hash, or P2PKH, is the SegWit version of P2PKH, introduced in BIP 141. The key difference is that signature data is moved from the ScriptSig to a separate witness structure. This provides several benefits. It fixes transaction malleability by separating signature data from the transaction hash calculation, reduces transaction fees because witness data has a 75% discount in block weight calculations, and enables the Lightning Network by ensuring transaction IDs can't be changed before confirmation. P2PKH transactions use Bech32 addresses starting with BC1 on mainnet. The transaction structure differs significantly between P2PKH and P2PKH. In P2PKH, the signature and public key are in the ScriptSig of the input. In P2PKH, the ScriptSig is empty and the signature and public key are in the witness field. The ScriptPubKey for P2PKH is also different. Instead of the OP-OP-160 sequence, it is simply OP0 followed by the 20-byte public key hash. Despite these structural differences, the security model is identical. Nested SegWit, using P2PKH in P2SH, provides backward compatibility. Since not all wallets and services immediately supported native SegWit addresses, nested SegWit wraps a P2PKH output in a P2SH output. This allows SegWit benefits while using addresses that all wallets can send to. Nested SegWit addresses start with 3, like regular P2SH addresses, but when spent, they reveal a witness program that enables SegWit features. The downside is slightly larger transaction sizes than native SegWit. Taproot, or pay-to-taproot defined in BIP 341, is Bitcoin's newest transaction type activated in November 2021. It uses Schnorr signatures instead of ECDSA, enabling signature aggregation and more efficient multi-signature setups. Taproot addresses start with BC1P and provide better privacy by making complex spending conditions look identical to simple payments on the blockchain. Taproot also enables more sophisticated smart contracts through the MAST structure. However, wallet support is still growing, and many services do not yet support sending to Taproot addresses. Choosing between transaction types involves trade-offs. Use P2PKH for maximum compatibility with older wallets and services, though it is becoming less common. Use P2PKH for the lowest fees and modern features like Lightning Network compatibility. Use P2SH for multi-signature or other complex spending conditions. Use Taproot when privacy and advanced features are priorities, and all parties support it. As Bitcoin evolves, newer transaction types generally offer improvements, but adoption takes time across the entire ecosystem. Conclusion and key takeaways. We've covered an extensive amount of technical detail about P2PKH transactions, from the cryptographic foundations through the complete transaction lifecycle. Let's summarize the key concepts and their practical implications for working with Bitcoin. P2PKH transactions demonstrate Bitcoin's elegant balance between security and simplicity. By using public key hashes instead of raw public keys, Bitcoin provides an additional security layer that's particularly valuable given the long-term nature of blockchain storage. The use of standard script templates ensures that most transactions can be validated efficiently while still providing the flexibility of a programmable scripting system. Understanding the transaction structure, from version numbers and inputs through outputs and lock times, is essential for anyone building Bitcoin applications or troubleshooting transaction issues. Each field has a specific purpose and format that must be followed exactly. The distinction between the signing process and the verification process highlights Bitcoin's asymmetric cryptography. Signing requires the private key and is done once by the sender, while verification uses the public key and is performed independently by every node in the network. The script execution model, with its stack-based virtual machine and specific sequence of operations, provides security through deterministic behavior and limited complexity. While Bitcoin script is less flexible than Turing-complete smart contract languages, this limitation is actually a security feature that makes Bitcoin transactions easier to reason about and audit for correctness. Security best practices like avoiding address reuse, using compressed keys, and implementing proper key management are not just theoretical concerns but practical requirements for safely using Bitcoin. The multi-layered security model, combining elliptic curve cryptography with hash functions and script validation, has proven robust over Bitcoin's 15-plus year history. As Bitcoin continues to evolve with new transaction types like SegWit and Taproot, P2PKH remains relevant for understanding Bitcoin's foundations. Many of the concepts we've discussed, such as UTXOs, signatures, and script execution, apply across all transaction types. The skills you've developed in understanding P2PKH transactions will transfer directly to working with more advanced Bitcoin features. Whether you're developing wallet software, building Bitcoin applications, or simply wanting to understand how your Bitcoin transactions work at a deeper level, the detailed knowledge of P2PKH transactions provides a solid foundation. Remember that Bitcoin is ultimately a consensus system where thousands of independent nodes verify every transaction using the same rules, and understanding these rules empowers you to participate in this global, decentralized financial network with confidence. Thank you for your attendance. Please consider subscribing to the channel.